Welcome to this coding problem walkthrough. Today, we'll be solving problem number 467, titled Unique Substrings in Wraparound String. We'll explore the problem statement, understand the challenges, and break it down step by step. Let's dive in and tackle this together. The problem asks us to find the number of unique non-empty substrings of a given string P that exist in an infinite wraparound string. This wraparound string, denoted as S, is essentially the lowercase English alphabet arranged cyclically, meaning after Z, it wraps back around to A. For example, a substring like zizab would be valid in this wraparound string because it respects the cyclic order. The input for this problem is a string P composed of only lowercase English letters, and the output is an integer representing the count of such substrings. To clarify how this works, let's go through some examples. In the first example, the input string P is simply A. The only substring we can form from this is it itself. Since it is part of the wraparound string, the output is 1. In the second example, the input string is CAC. Here, the substrings are C, A, and CA. Among these, C and A are valid because they exist in the wraparound string as individual characters. However, CA is not valid because the character C does not directly follow A in the cyclic order. As a result, the output for this example is 2. To elaborate further, when we look at the third example, where the input P is ZAB, we see that the substrings are Z, A, B, ZA, UB, and ZAB. All of these are present in the wraparound string because they respect the cyclic order. For instance, ZA is valid because after Z, the letter appears in the wraparound string, and ZAB is valid because the sequence Z to A to B is cyclically continuous. Therefore, there are 6 unique substrings in this case, and the output is 6. Finally, let's consider some important constraints and edge cases. The length of the input string P can be up to 10,000 characters, so efficiency is key. If P contains only one character, the output is always 1, since any single letter is part of the wraparound string. For strings with repeating characters, such as AAAA, the substrings are limited by the length of consecutive runs. For example, you can have a AA, AAA, and so on, up to the length of the run. Additionally, if the characters in P break the cyclic order, such as AC, the sequence is interrupted, and substrings must be calculated separately for each segment. These considerations are crucial for solving the problem effectively. To solve this problem, one approach we might consider is a brute force method where we generate all possible substrings of the input string P. The intuition here is straightforward. We check if each of these substrings exists in the infinite wraparound string, which is essentially the alphabet repeated infinitely. To do this, we would generate all substrings of P, then verify for each substring whether its characters follow the wraparound condition. For example, the character A must follow Z in the infinite sequence, and all consecutive characters in the substring must maintain their natural order. Once verified, we store these substrings in a set to ensure uniqueness, and the final answer would simply be the size of this set. However, this method is computationally expensive. Generating all substrings takes O(n squared, and verifying each substring adds another layer of complexity, resulting in an overall time complexity of O(n cubed). This makes the brute force approach impractical for larger strings, and it also consumes additional space to store all substrings, which further limits its scalability. A much more efficient solution involves using a dynamic programming approach combined with character tracking. Instead of generating all substrings, the key idea is to focus on the maximum length of unique substrings that end with each letter of the alphabet. Once we have these lengths, we can calculate the total number of unique substrings simply by summing them up. The observations that drive this approach are as follows. In the infinite wraparound string, the characters follow a strict cyclic order, such as ziziptifgijhulnapkristuvuksis. The problem essentially boils down to finding all substrings within P that follow this order. Importantly, the longest substring ending at a given character inherently includes all shorter substrings that end at the same character. To implement this, we use an array count of size 26 to store the maximum lengths of substrings ending with each letter from A to Z. We also maintain a variable max_len to track the current length of a valid wraparound substring as we iterate through P. When the current character continues the wraparound sequence from the previous character, we increment max_len. If it doesn't, we reset max_len to 1. For each character, we update the corresponding index and count with the maximum value between its current stored length and max_len. Finally, the result is simply the sum of all values in the count array. This optimized approach has a time complexity of O(n), as we only need to iterate through the string p once. Additionally, it uses only O(1) extra space, since the count array has a fixed size of 26 regardless of the input length. This makes the solution highly efficient and scalable. We chose this approach because it significantly outperforms the brute force method, both in terms of time and space complexity. Instead of generating and storing substrings, it directly calculates the contribution of each character to the total count, leveraging the wraparound structure of the problem. The key insight here was recognizing that we only need to track the maximum length of substrings ending at each character, which eliminates redundant computations and simplifies the process. While the brute force approach may seem simpler conceptually, it becomes infeasible for larger inputs due to its cubic time complexity. The dynamic programming approach, on the other hand, requires a deeper understanding of the problem but achieves linear time complexity, making it the ideal solution. It strikes the perfect balance between efficiency and clarity, and this is what makes it the best strategy for this problem. To solve this problem, we need to determine how many unique non-empty substrings of the input string p are also substrings of an infinite wraparound string. The wraparound string is essentially the alphabet repeated infinitely in sequence, such as zizipdifgij. A substring meets the wraparound condition if, for every 2 consecutive characters, the second character directly follows the first alphabetically, or if the first character is z and the second is a, completing the wraparound. Instead of using brute force to generate all substrings, which would be computationally expensive, we take a smarter approach. Specifically, we track the longest valid substrings ending with each character, as this gives us all the unique substrings in a more efficient way. This idea is the core of our optimization. We'll achieve this by using a sliding window technique, which allows us to traverse the string efficiently while maintaining the length of the current valid substring and updating a record of the longest substrings for each character in the alphabet. The key to this approach is recognizing when a character in the string extends the current valid wraparound substring. If the current character p(i) continues the pattern established by the previous character p(i1), we increase the length of the current valid substring. Otherwise, we reset the length to 1, indicating that the substring starts anew. For each character, we update an array max_len, where each index corresponds to a letter in the alphabet, using the maximum length found so far for substrings ending with that character. Once we've processed the entire string, we can calculate the total number of unique substrings by summing up all the values in max_len. This method avoids redundancy by focusing only on the longest substrings that satisfy the wraparound condition, rather than generating all possible substrings. The sliding window approach ensures that we process the string linearly, making the algorithm efficient. The condition, ord p(i), ord p(i1) == 1, ord p(i1) == z and p(i) == a, helps us handle both regular consecutive characters and the special wraparound case from z to a. Now, let's break down the algorithm into pseudocode. We start by initializing the max_len array with 26 zeros, 1 for each letter of the alphabet, and set current underscore length to 0. Then, we traverse the string p. For each character, we check if it extends the wraparound substring from the previous character. If the condition is met, we increase current underscore length. Otherwise, we reset it to 1. Next, we calculate the index of the current character in the alphabet using ord p(i), ord a, and we update the corresponding value in max_len by taking the maximum between its current value and current underscore length. After traversing the string, the result is simply the sum of all values in max_len, which gives us the total number of unique substrings. This pseudocode highlights how we efficiently track and update the longest substrings for each character while ensuring linear time complexity. Analyzing the complexity of the algorithm, we see that the time complexity is O(n), where n is the length of the string p. This is because we traverse the string once, and each update to the max_len array is performed in constant time. The space complexity is O(1) in terms of additional space, as the max_len array has a fixed size of 26 regardless of the input size. Let's consider some edge cases to ensure robustness. If the input string is empty, the result is 0 since there are no substrings. For a single character string, the result is always 1 because the single character itself forms the only substring. In cases where all characters are identical, such as AAAA, the result will be the length of the string since each prefix of the string forms a unique substring. Finally, for strings without wraparound transitions, such as ABCs, the algorithm correctly handles transitions like XYZ wrapping back to a. For example, if the input is p equals zab, we initialize max_len to an array of zeros and current_length to 0. As we traverse, we calculate the valid substring lengths for z, a, and b, updating max_len accordingly. For the input p equals zab, we process each character step by step. At I equals 0, the character is z, so current_length becomes 1, and we update max_len, 25, to 1. At I equals 1, the character is a, and since it wraps around from z, we increment current_length to 2 and update max_len, 0, to 2. At I equals 2, the character is b, which is consecutive to a, so current_length increases to 3, and we update max_len, 1, to 3. Finally, we sum up the values in max_len, which gives us 1 plus 2 plus 3 is equal to 6. This means the total number of unique wraparound substrings is 6. By focusing only on the longest substrings for each character, our algorithm efficiently calculates the result without redundant computations, ensuring both correctness and optimal performance. The solution to LeetCode problem number 467, unique substrings in wraparound string, is implemented in the above Python code. Here's how it works. We aim to determine the number of unique non-empty substrings of the given string p that also exist in an infinite wraparound string, a continuous cyclic sequence of the English alphabet. Step-by-step explanation. 1. Initialization. We start by creating a dictionary max_len to store the maximum length of valid substrings ending with each character, a to z. Each letter is initially mapped to 0. 2. Iterate through the string. We traverse the input string p to determine the length of the current valid substring ending at each character. If the current character continues the wraparound pattern of the previous character, e.g., a to b, or z to a, we increment the current substring length, current_length. Otherwise, we reset current_length to 1, as the wraparound sequence is interrupted. 3. Update maximum lengths. For each character p, I, we update the maximum length of substrings ending at that character in the max_len dictionary. This ensures we only count the longest valid substring for each character, avoiding duplicates. 4. Calculate the result. Finally, the result is the sum of all values in max_len, representing the total number of unique substrings. Key observations. The wraparound nature of the string is handled using the condition, ord, p, I, ord, p, id1 equals 1 or p, id1 equals z and p, I equals of, which checks for consecutive letters with the z to a transition. By storing only the maximum lengths for each ending character, we efficiently avoid counting duplicate substrings, keeping the solution optimal. Complexity analysis. Time complexity, O, n, where n is the length of the string p. We process each character once. Space complexity, O1, as the max_len dictionary has a fixed size of 26. This solution is efficient and directly addresses the problem requirements, ensuring correctness and optimal performance. Here, we start by defining the find substring in wraparound string method, which takes a string p as input. The goal is to determine the total number of unique substrings in the infinite wraparound string of the alphabet. First, we initialize an integer array maxlen of size 26 to store the maximum lengths of substrings ending with each letter from a to z. This will help us track the contribution of each letter to the final result. We also declare a variable current length to keep track of the length of the current valid substring sequence. Then, we iterate through the string p using a for loop. At each step, we check whether the current character continues the wraparound sequence. A valid continuation occurs if the difference between the current and previous characters is 1, or if the sequence wraps around from z to a. If it's a valid continuation, we increment current length, otherwise, we reset it to 1. After this check, We calculate the index of the current character in the alphabet and update the maxlen array for that character by taking the maximum of its current value and current length. Finally, to compute the result, we sum up all the values in the maxlen array. Each value represents the total unique substrings that end with a specific character in the wraparound string. The method then returns this sum as the result. This approach ensures that we account for all unique substrings efficiently, leveraging the maxlen array to avoid redundant calculations. The solution runs in O(n) time, where n is the length of the input string, making it highly efficient for this problem. To solve this problem, we start by initializing a dictionary called max_len with all lowercase letters as keys, each set to an initial value of 0. This dictionary will help us track the maximum length of substrings ending with each letter. Additionally, we initialize current_length to 0, which will keep track of the length of the current valid substring as we iterate through the string. Looking at the first example where the input is p equals zab, we begin by processing the characters one by one. For the first character, z, since it is the starting character, we set current_length to 1. We then update max_len, z, to the maximum of its current value, which is 0, and current_length, resulting in max_len, z, equals 1. At this point, the max_len dictionary reflects that the longest substring ending in z has a length of 1, and the current_length is 1. Next, we move to the second character, a. Since a follows z in the wraparound alphabetical order, we increment current_length to 2. This means we now have a valid substring of length 2 ending at a. We update max_len to be the maximum of its current value, which is 0, and current_length, which is 2. This results in max_len equals 2. Moving to the third character, b, we observe that b follows a in the wraparound order. Thus, we again increment current_length, this time to 3. Now, we have a valid substring of length 3 ending at b. We update max_len, b, to the maximum of its current value, 0, and current_length, 3. This gives us max_len, b, equals 3. At this stage, the max_len dictionary reflects the longest substrings ending in z, a, and b as 1, 2, and 3, respectively. Finally, to calculate the result, we sum all the values in max_len, which gives 1 plus 2 plus 3 equals 6. This is the total number of distinct substrings in the wraparound string for this input. Now, let's consider the second example, where the input is p equals cac. We start by reinitializing max_len so that all values are 0, and current_length is reset to 0. As we analyze the string, the first character, c, is the starting character, so we set current_length to 1. We then update max_len, c, to the maximum of its current value, 0, and current_length, resulting in max_len, c, equals 1. At this point, the max_len dictionary indicates that the longest substring ending with c has a length of 1, and current_length is 1. Next, we look at the second character, a. Since a does not follow c in the wraparound alphabetical order, we reset current_length to 1. This means we are starting a new valid substring that ends at a. We then update max_len to the maximum of its current value, 0, and current_length, so max_len equals 1. When we move to the third character, c, we see that c does not follow a in the wraparound order. As a result, current_length is reset to 1 again. We then update max_len, c, which already has a value of 1, to be the maximum of 1 and current_length, so it remains max_len, c, equals 1. After processing all the characters in the string, the max_len dictionary shows that the longest substrings ending in c and a both have lengths of 1. To calculate the result, we sum the values in max_len, which gives 1 plus 1 plus 1 equals 3. This is the total number of distinct substrings in the wraparound string for this input. Now, for the third example where the input is p equals abcdzab, we again start with max_len initialized to 0 for all letters, and current_length set to 0. For the first character, a, being the starting character, we set current_length equals 1. We then update max_len to the maximum of its current value, 0, and current_length, resulting in max_len equals 1. Next, we process the second character, b. Since b follows a in the wraparound order, we increment current_length to 2, indicating that we now have a valid substring of length 2 ending at b. We update max_len, b, to the maximum of its current value, 0, and current_length, so max_len, b, equals 2. For the third character, c, which follows b, we increment current_length to 3. This means we have a valid substring of length 3 ending at c. We update max_len, c, to the maximum of its current value, 0, and current_length, resulting in max_len, c, equals 3. For the fourth character, d, which follows c, we increment current_length to 4. This represents a valid substring of length 4 ending at d. We then update max_len, d, to the maximum of its current value, 0, and current_length, giving max_len, d, equals 4. When we reach the fifth character, z, we notice that z does not follow d in the wraparound order. As a result, we reset current_length to 1 and update max_len, z, to the maximum of its current value, 0, and current_length, so max_len, z, equals 1. At this point, the max_len dictionary reflects the longest substrings ending in a, b, c, d, and z as 1, 2, 3, 4, and 1, respectively. For the sixth character, a, we see that a follows z in the wraparound order, so we increment current_length to 2. We update max_len, to the maximum of its current value, 1, and current_length, resulting in max_len, equals 2. Finally, for the seventh character, b, which follows a, we increment current_length to 3. We then update max_len, b, to the maximum of its current value, 2, and current_length, so max_len, b, equals 3. After processing all the characters, the max_len dictionary shows that the longest substrings ending at a, b, c, d, and z have lengths of 2, 3, 3, 4, and 1, respectively. Summing these values gives 2 plus 3 plus 3 plus 4 plus 1 equals 13. This is the total number of distinct substrings in the wraparound string for this input. In this algorithm, we process the input string p in a single pass. To start, we initialize the max_len dictionary with all lowercase English letters from A to Z as keys, and their values set to 0. This initialization step involves iterating over 26 letters, which takes constant time and contributes a complexity of 26, which simplifies to 1. Next, as we iterate through the input string p of length n, we perform several constant time operations for each character. These operations include checking if the current character continues the wraparound sequence, updating the current_length variable, and modifying the max_len dictionary for that character. Since we only make a single pass through the string and handle each character independently in constant time, the time complexity for this step is n. After iterating through the string, we perform a final summation over the values stored in the max_len dictionary. Since the dictionary contains only 26 keys, this summation operation also takes constant time, contributing a complexity of 26, which simplifies to 1. When we combine all these steps, the overall time complexity is dominated by the iteration over the input string p, resulting in a final time complexity of n. For space complexity, the max_len dictionary holds one entry for each lowercase English letter, requiring fixed space of 26, which simplifies to 1. Other auxiliary variables, such as current_length and loop indices, also use constant space. Since no data structures scale with the size of p, the overall space complexity is 1. To better appreciate the efficiency of the optimized approach, consider a brute force solution. A naive method would generate all possible substrings of the input string p and check each substring against the wraparound condition. Generating all substrings takes n squared, and checking each substring's condition takes k, where k is the substring length. In the worst case, this results in a total time complexity of n cubed. Additionally, storing all substrings could require n squared space. In contrast, the optimized algorithm avoids generating substrings entirely. By directly calculating the maximum length of valid substrings ending at each character in a single pass, the time complexity is reduced to n, and the space complexity is reduced to 1. we can formally verify the optimized algorithm's time and space complexities. The algorithm processes the string p exactly once, performing constant time operations for each character. As a result, the time complexity scales linearly with the size of the input, giving us O(n). The initialization and summation over the fixed size max_len dictionary only add constant overhead, which does not affect the overall complexity. For space complexity, the max_len dictionary is fixed at 26 keys, and no other space depends on the size of p. Therefore, the space complexity is O(1). Considering best, average, and worst-case scenarios, the time complexity remains linear. Whether all characters are the same, the input is random, or the entire string forms a valid wraparound substring, the algorithm processes all n characters in O(n) time, while the space complexity remains constant at O(1). In solving problems involving wraparound strings, there are several common mistakes to watch out for. One of the most frequent errors is not handling wraparounds correctly. For example, when transitioning from Z to A, it's easy to overlook the circular nature of the alphabet. This transition must be explicitly accounted for in your solution logic. Another issue is relying on brute force methods, such as generating all possible substrings and checking each one for wraparound validity. While this approach might work for small inputs, it becomes computationally expensive as the input size grows, leading to inefficiencies. Additionally, failing to optimize for repeated substrings is a common pitfall. Remember that longer valid substrings inherently include shorter ones, so you should avoid redundant calculations. Lastly, don't ignore edge cases. Consider scenarios like single-character strings, strings without valid consecutive characters, or strings consisting only of wraparound transitions like ZA. Testing these edge cases ensures your solution is robust. Another common mistake is misunderstanding the problem constraints. For instance, assuming that the input string can be arbitrarily large or overlooking the fact that it consists only of lowercase English letters can add unnecessary complexity to your solution. When approaching wraparound string problems, it's crucial to focus on patterns in consecutive characters. A key observation is that the difference between two consecutive characters in the alphabet, when taken modulo 26, can reveal the wraparound nature of the string. This insight simplifies the logic significantly. To optimize your solution, leverage efficient data structures like arrays or hashmaps to store the maximum length of valid substrings ending at each character from A to Z. This minimizes redundant computation. When discussing your solution with an interviewer, be clear about trade-offs. For example, you might start by explaining the brute force approach, highlighting its inefficiencies, and then describe how your optimized approach overcomes these challenges. Finally, modular arithmetic is a powerful tool for wraparound problems. Using calculations like ORD C2, ORD C1, plus 26, %26 can make character transitions easier to handle. When tackling this problem, it can be helpful to explore related challenges to build a deeper understanding. Examples include LeetCode 3, which focuses on the longest substring without repeating characters, and LeetCode 5, which involves finding the longest palindromic substring. Problems like LeetCode 159, which deals with substrings containing at most two distinct characters, can also provide valuable insights. In terms of alternative approaches, dynamic programming is a powerful method to solve wraparound string problems. This technique uses extra memory, such as a hash map or array, to store intermediate results, but it's far more efficient than brute force, achieving O(n) time complexity. Another useful strategy is the sliding window approach, which enables efficient identification and counting of substrings. While this method is also O(n), it can be more challenging to implement for wraparound problems due to the additional logic required to handle transitions like Z to A. Both approaches have their trade-offs, and understanding these can help you choose the most effective solution for the given constraints. A third approach to solving wraparound problems involves leveraging mathematical or modular insights. By deeply understanding modular arithmetic, you can significantly simplify the logic required to handle wraparounds. For instance, using modulo operations to calculate character transitions ensures that you maintain correctness while minimizing complexity. The trade-off here is that this approach requires a strong grasp of the underlying mathematical principles, but the payoff is an elegant and often more efficient solution. With careful implementation, this method can achieve O(n) complexity or better, making it a highly effective strategy for handling large input sizes. This mathematical perspective can complement other techniques like dynamic programming or sliding windows, giving you a versatile toolkit for tackling this class of problems. Great job on finishing this problem. To summarize, we tackled the unique substrings in wraparound string with an efficient approach using dynamic programming. We learned the importance of identifying patterns and leveraging constraints. Thanks for watching, and don't forget to practice similar problems to strengthen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!